Yeah, okay. All right. Nice to be here. I am from a slightly different community, but I think the issues you're discussing here are very interesting. And I hope now that interest is a bit commutative. I'll try to make it interesting, at least for you. So my community is ADS CFT holography, but I think there are important and unexplored, I should say, points of connection, and I'm very curious about those. So let's see. All right. I start with a takeaway, so we'll get at least something out of this talk, hopefully. So I claim then that standard quantum mechanics, at least in the form of quantum field theory, can model, I'm not saying it is actually quantum effects of quantum gravity, but it's a useful set of models. It provides a useful set of models. That's my first claim. And in this context, I've found that composite objects, well, we know that. They probe tidal effects of gravity. We know that because the moon and the Earth are composite objects, and they definitely show tidal effects. But even more interesting for us here, perhaps, this holds at a quantum level as well. Finally, I will not say black holes, but black hole-like objects can also be modeled in this framework by looking at thermal equilibrium. And in a particular environment, what I would call a gravitational cavity, which we call, in this field, we call that anti-de Sitter space. Of course, it's interesting to go beyond thermal configuration, thermal equilibrium, and consider pure states and how they are entangled, and if eventually you can thermalize, etc. There is some work on this, but I will not discuss that, and also I will not discuss the radiation. I would have wanted to, but it got too complicated. It will be an exercise for next time, I think, because I think I have to cover some material in, a crash course in 5 minutes or so on holography. That is a field that has developed for 20 years. I think it's possible, but let's see if I can do it. All right. Yeah, this is the idea that, yeah, it does look a little bit grayer on the, there's not much difference, but the middle item here, composite objects, is I thought was, I mean, I saw similar things in the abstract, so I wanted to connect to that because it's very natural in this framework. And what you can see is how objects coming in states are in one state and out states are in another internal configuration. This is what tidal effects do. They convert one state to another one, which is pretty nice as a way to detect the presence of interesting gravitational fields. All right. So what do I want to do with this talk, and what do I don't want to do with my research in this field? Well, I like a kind of operational approach. Define gravity, not by some unobservable object like a gravitational field, right? The gravitational field is not observable. We all know that, or we should know it. It's not directly observable. It's like a gauge field. Depends on coordinates. etc., etc. So define gravity by measurable quantities. I would say, what is a measurable quantity? It could be Green's functions of a quantum field theory, for instance. Related to this, with some background independence, it's difficult in gravity to distinguish between what gravity is and what is our choice of reference frame or system. So the safest way to me is to look and do the actual measurements at weak fields, which is usually at infinity, far away from the sources of gravity. Then you're pretty safe. This is a time-honored principle in, the origins of my field is particle high energy physics, scattering theory. And there's still some truth in it, right? Even if it's old, it can be some truth. Now, as I said, I want also to probe gravity by composite objects. And for me, they will be represented by composite quantum field theory operators. I've crossed over Unruh de Witt, and that's not really kind, is it? I think it's a brilliant idea. I'm sure, yeah. I think we need alternatives. Let's put it that way. What I will replace them will certainly have deficiencies, but again, there are different perspectives, and maybe having different perspectives can help getting a better picture of the whole field. All right, again, as I said, reliable detection in asymptotic regions, that's what I'm going to focus on. Detectors of composite objects, well, in a way they're more composite. They have more states, just like in the previous talk, an infinite number of states in my case, but you will only access a few of them in practice, of course. Yeah, the detectors in this case are very quantum, right? So it's violating some principles that are cherished, but it can also lead to interesting. I mean, of course, objects are quantum, so it's fine, right? But it will be a bit different. So, for instance, I will not specify trajectories for the detectors. They will propagate just like any particle. They are particles in a sense. Particles that can be excited. That's my detectors. They can be detected by ordinary means out at infinity. And moreover, detectors are made of the same stuff as the fields that they detect. This is both a consistency condition, but also very annoying at times because you have very little freedom in building your tools. But that's it. So the idea is to represent gravity by quantum field theory. And that's done in this subfield of high energy theory that is called ADS-CFT. So what is that? It's an observation connecting results in gravity and quantum field theory from 1997 or 1998. And it's still a conjecture. Although evidence for it has been accumulating steadily. And there is not really any counterexample. There may be a few doubts here and there about the scope and various things, but it's actually extremely successful to the extent that it's becoming a bit boring. But it's a body of knowledge that is quite extensive today. And we can make use, I will not make use of all of it, definitely. I will also not show you all the calculations. But trust me, the part I'm using of this body of knowledge is quite simple. And what are the simplest fact of these? What is ADS? It's anti-de Sitter space, if that tells you anything. And CFT is conformal field theory. So let's talk about these things for a moment. Well, I think ADS is essentially the gravitational equivalent of a harmonic oscillator. It's sort of the simplest space-time that confines a particle. It has constant negative curvature, and it confines the motion of all waves and all massive particles. That is good for some things, as a theoretical laboratory. It's not so good for the Hawking radiation that I avoided. That's why I avoided it. Of course, you can technically deal with it, but it will become complicated. And because it confines, it's effectively a cavity, which is good for thermodynamics, for instance, and also for quantum mechanics. It's just quantum mechanics. And ADS has a natural conformal structure at infinity. That is math lingo for that. You can control light propagation in a simple way. Here is just a picture showing spatial slices, that's constant time surfaces. It's a hyperboloid, essentially for time-like vectors in Minkowski space. That has the same geometry as ADS. But then you usually, when I draw things, and I will do that several times, I've already secretly drawn things for you. I've drawn the spatial slice as a disk. Straight lines or geodesics on that time slice are actually circles which are orthogonal to the boundary. That's the geometry. We don't need that in detail. I just wanted to show that this is concrete. It's a very simple structure. And spatial infinity will be like a sphere at infinity out there. Okay. All right. That was ADS. That's all I will tell you about on ADS. Conformal field theory. Conformal field theories are the simplest interacting quantum field theories in many sense. They don't have an energy, they don't have a scale in themselves. They can get a scale when you put them on certain geometries, but they don't have an intrinsic scale. They require not a metric or way of measuring distances, but angles or light rays. Then they can do well. They are defined by spectrum, like any quantum theory. I will not, by the way, this is just to show you that there is a framework here. I will not use details of this, except that there is a spectrum of operators that are interesting in each conformal field theory, characterized by spin and the quantum number that is like energy, but it's scaling dimension, actually, because there is no scale as such. And then all the interactions in this theory are characterized by couplings of 3 operators. That's all. That defines everything about this conformal field theory. So it is simple. Actually, the theories I really use are going to be free field theories. So I don't have to deal with all this structure in the calculations behind what I'm telling you about in the actual examples. Yeah. That was CFT and that was ADS. And what is ADS CFT? That is this connection between the two. The geometry in ADS is such that out at infinity we have a sphere. On that sphere we have a conformal structure. You can have a conformal field theory. So everything that happens on the boundary out here. Now, remember, this is infinitely far away, but I use this this like stereographic projection to a disk. If we are interested in the kind of processes I talked about, namely things that are happening far out at infinity, where the gravitational fields are weak, if we do that, we can make use of this to the full extent. And out there, it's quite easy. Was the first things that were done in this field that you could match operators in on the sphere with fields inside of ADS, one-to-one. That's a dictionary. So that means that Green's functions, at least asymptotic Green's functions of the asymptotic regions of anti-de Sitter space are directly related to other Green's functions in the conformal field theory. So let me repeat that. There's a direct mapping between Green's functions in gravity that we are interested in and quantum field theory, standard quantum field theory, only that is on a sphere. So we want to calculate these Green's functions of certain operators and obtain sort of a scattering theory in anti-de Sitter. That's the idea. It's here, right? Operator out here, operator out there, in, out. That's like a scattering process. What happens in between? That is mediated by anti-de Sitter space, but it can also be calculated directly in a quantum field theory. So, yeah, so to get back to the takeaways, there is a connection, hopefully, between the takeaways and the content here. I've been saying that standard quantum mechanics in the form of quantum field theory can model quantum effects of gravity, for example, around black holes. Right? There was a check mark there. All right, black holes. Black holes have an event horizon. My point here is really that the most interesting thing with black holes are, and the most things that is going to survive, is really not a horizon, because it's not clear that there are horizons in the quantum theory. But there are going to be photon spheres where photons can make circles around, a bit outside the horizon. So whether there is a horizon or not is not clear, but there is something else interesting that can be studied, and it can be studied in quantum field theory, as I've been claiming. So how do you make black holes in this quantum field theory? Well, we know that black holes are thermal objects in a sense. They emit Hawking radiation, they have entropy. In flat space, thermal equilibrium is unstable because temperature actually decreases with mass. In ADS, at least if they are big enough, black holes are stable, and that happens above a certain Hawking page phase transition. That phase transition does have a match in quantum field theory as well, so this whole structure survives. That's the point. ADS is also good for thermodynamics, since we have no divergences from counting of states because we have a nice box cavity. All right. So we got black hole-like objects. Now we want to study composite objects as probes. Well, test particles are not so interesting themselves, but if they are composite, they are more interesting. They are clocks, and I think Igor and Magdalena and others here have been making a lot of progress on looking at this. So the clocks will sense gravitational time dilation. But if you also look at their internal structure, they experience tidal forces. That can be studied in this framework, and that will fulfill the next checkbox. We can tie this together by considering these composite operators in quantum gravity. Now it's getting fast and sketchy. Composite objects are actually dipoles. You can study dipoles. They have internal excitations. To do that technically, you have to take a few limits. Make it messy, but makes it possible to calculate Green's functions between the lowest state, which is, I written that up, is the density essentially, and energy density. It's the lowest excited state. And if you calculate such a correlation function on the boundary, you will get the tidal excitation of a probe traveling through space. This depends on temperature. And therefore you can also see the effects of black hole-like states on tidal effects. Here they are. We can transform to momentum space, and I suppose the outcome is that higher temperature or mass yields conversion at smaller angles, which actually means that the object, black hole-like object, is larger, as you can see by considering what geodesics are in this asymptotic space. They are like circles which are orthogonal to the boundary. So if you have smaller angles, getting conversion between nearby points, smaller circles, means that the object that disturbs the propagation is larger and larger, forcing the gravitational effects closer and closer to this boundary. Yeah. Behind all of this is free quantum field theory with the constraint that you are dealing with charges, right, on a sphere. So it's super important to find all these effects in detail to impose the Gauss law constraint. Once you've done that and do all your partition sums, correlation functions in free field theory, those correlation functions I showed you drop out, and you find these nice results. Other results too that connect free quantum field theory with a large number of charges, colors, whatever you call it, fields, is similar to gravity. Not exactly gravity, but similar. And, well, you've seen these conclusions before, so I will not repeat them. But this is a framework, at least. It would be interesting to see how it connects with more this is not proper quantum measurements, but we have a framework at least. Thank you.